So now we have another kind of a device which is called a JK flip-flop. So let us kind of organically understand that why do you need another flip-flop, another kind of flip-flop, and what is their architecture and what are the drawbacks and so on. So let us start. So till now we started with a SR latch, then we moved on to D latch, then we moved on to a D flip-flop. Okay, so same thing we have here. It started with an SR or RS latch, and we saw that it had issues, particularly with respect to the 0 input, right? And you can always use this thing with a write enable, right? So you can have something that has an enable input which basically turns on or turns off the SR latch, but still it is going to have its issues, right? The 1-1 combination is memory hold, just for your revision. 1-0 or 0-1 is used for setting or resetting the circuit, but 0-0 is the forbidden state, right? So 0-0 is something which was not allowed in a SR latch. Okay, so this is the same as SR latch, just that there is an extra write enable, so don't worry about it. And we have a NAND gate here just to make sure that the write enable works. If you put 0 here, this is going to be 1, right? If you put a 0 here, it is going to be 1, and this is also going to be 1, which basically indicates a memory state. Okay, so we needed a NAND gate there. So this is just S bar. Okay. So don't worry, this is not a new kind of latch or new kind of flip-flop. This is a RS latch only, and these are the issues with the RS latch that we have already faced earlier. Okay, so the first solution was using a D input and make sure that D and D bar are supplied to the top and the bottom NAND gates. So in the first NAND, if we are supplying a value of D, we are making sure that we are giving a input of D bar. Okay, so in that case, what could happen is that 0-0 state could be avoided, but nothing else, right? So SR latch will now function reliably. It is not going to go into a forbidden state. Okay. But in that case, we are losing the functionality to some extent, given that we are only having one input. Earlier, in case of SR latch, we are having two inputs. In this case, if you are putting 0, you are getting an output of 0. If you are putting 1, you are getting an output of 1. Okay. But whereas in ISR latch, where there are two inputs, so you could have potentially given more number of combinations. So this is called the gated D latch on the left hand side. So you have a clock input. So this is the clock input which is acting as the write enable. You can call this as the write enable function, and this is the NOT that is required for D, right? So this is your D, this is your D bar. Okay, and this is a basic SR latch. This is your RS latch. Okay, so one more extra feedback could be actually given from this Q to the top two NAND gates. So this input, this output could be actually going back as a actually it is going to come down. It is going to go as a feedback to one of the inputs here. Okay, similarly this Q bar is going to go as a feedback to one of the inputs here. So this is a new kind of a flip-flop which is called a JK flip-flop, and it has two inputs J and K. So let us see how this looks like. This is exactly similar to whatever we have seen in case of a gated D latch. So the clock is the same, as you can understand, and instead of D and D naught, we are actually having two different inputs J and K. So earlier J and K was D and D bar, as you can very clearly see. D was directly input, which is nothing but your proxy for J, and then you had D bar, which is again K, right? Instead of having a NOT gate like that, we are having this extra inputs also now. And what is the other thing that we have? The other thing is that look at this feedback connection. There is a Q is actually being fed back to the second NAND gate, the lower NAND gate, and this output Q bar is being fed to the top NAND gate with J. Okay, so we can start analyzing that what are the different properties this JK flip-flop might have. So a lot of things could be done using D also, because D is extensively used, just that the JK is going to give you some extra flexibility because there are two inputs, right? Just because there are two inputs, you can do certain things with this. Here the clock was itself used as a write enable function. Here we can see what kind of, because if you have value in D, right, and your clock pulses through, if you have the clock high, it is going to write data during those periods of time. It can be done in a little bit more sophisticated way. Maybe there is a clock, that is fine, but we can make sure that even if there is clock, there is some other notion of enabling the gate or not enable or disabling the gate and so on, right? So which is a more explicit control for write enable. Just not instead of using the clock, you can do something else, or there are other things also that can be done, and with this J and K as input. So let us check one by one the different modes in which this JK flip-flop can operate. Okay, so one of the things is if J is equal to 0 and K is equal to 0, what will happen, right? This is your entire JK flip-flop, and let us say J is set to 0, K is set to 0, okay, and you have a pulsing clock, right? So the clock pulses, it is 0, 1, 0, 1 and so on. But since J is equal to 0 and K is equal to 0, this value must be equal to 1 here, right? And if you can see Q, this is Q, this is Q, right? So here you have Q, right? And here you have Q bar. Now you can take any values and test out what is going to happen. Okay, so let us say we have 0 here, right, which is Q equal to 0, right? I will not put too many things. Q is equal to 0, so Q bar is going to be equal to 1. Okay, so if Q bar is equal to 1 and Q is equal to 0 here, so as you can see from this feedback connection, this is 1, right? So this 1 is going to be coming here. This is also going to be 1. 1 and 1 is going to be 0, right? And the NAND output is going to be 1 and 1 is going to be 1. The NAND output is going to be 0. Okay, similarly you have 0 in the same line, and 0 is going to come here. 0 and 1 is 0, but we put a NAND, so this is equal to 1 only. So I'll mark the zeros line with the red color. Let's say this is your 0, this is 0, okay. This is 0 and the other line is 1, okay. So this line is 1. Okay, so this is how this is operating, and J is equal to 0, K is equal to 0. So if you have Q is equal to 0 and Q bar is equal to 1, definitely that is not going to change its value. Even if you try out the other way around, for example, I will swap these values. If I swap these values completely with J is equal to 0 and K is equal to 0, but Q now is going to be instead of 0, we can put it at 1. If we put this at 1, this is going to be 0. Okay, so you can apply the same logic. So if this line is 1 So the feedback here is also going to be 1, right, and this goes as 0, so that is not an issue, and this 1 is going to come down in this path as a 1. Okay, so these are all going to be fine. So this is 1 0 is there, so in this 0 0 mode it doesn't matter. If they are 1 0, the NAND gate output has to be 1. Okay, so if you have 1, this is coming as 1, 1 and 1 is 0, this becomes again 0, and this is, you can just, this was a revision, but you can think of this again as a RS latch, right, RS latch. So in the JK flip-flop, if J is equal to 0 and K is equal to 0, the R and S inputs are becoming 1. So this is basically going to act as a memory hold state. Okay, so this is going to act as a hold state or a memory state, which means that it is remembering the previous input. So Q and Q bar are not going to be changing depending on the value of J and K. If J and K is equal to 0 and 0, Q is going to be retained, and of course Q bar is also going to be retained. Okay, so this is a important thing to remember. So we are getting the functionality of a RS latch in some form. Okay, so in case of D, if you are putting 0, the output was definitely becoming 0. If you are putting 1, the output was definitely becoming 1. And just that if you do not have a clock, in that time only it is going to preserve the contents. But in this case, you can have the clock, doesn't matter. As long as you can have 0 and K being controlled, you can always retain the value. Okay, it doesn't matter if the clock is high or low, or it is edge triggered and so on, doesn't matter. Okay, so there could be more configurations. For example, we can have a situation where J is equal to 0 and K is equal to 1, right? So here we are saying that J is equal to 0 and K is equal to 1. So similarly, we can have these two cases. Q can be either 0 or Q can be either 1, or you can just work with the value of Q. Clock, we are assuming this is coming and enabled, right? If the clock is 0, definitely this is going to be 1, right? So that is a memory hold stage. So I'm not looking into clock is equal to 0. Clock we are assuming here is as 1. Okay, clock is equal to 0 is anyway logic low, so the output is going to be 1, output is going to be 1 here. So this is going to act as a RS flip-flop, RS latch with R and S both set to 0, R and S both set to 1, sorry. Okay, so if K is equal to 1 and here you are having Q, right? So you are having Q here, and here you are having Q bar. Okay, so what is the output of this line? The output of this line is going to be Q bar, right? So the output of this line is going to be Q bar. I will rather use the capital letters because that is what we have assumed. So this is Q, this was Q bar, this is coming from here, coming from all the way as a feedback, and this Q is coming via this line. Okay, so this is 1.1.Q, which is the AND, right? And the NAND is going to be Q bar, right? So this is going to be Q bar. What is the other input? The other input is basically Q. Okay, so if we put this configuration Q and Q bar, if you take a AND, this is going to be 0, right? And so the NAND of it is going to be 1. Okay, and similarly, if you have a 1 here, but you are also having a 1 here, right? Because this is 0, J is equal to 0, right? So 0, Q bar and 1, this is going to create a 0 is going to be the ANDed value, the NANDed value is going to be 1. So 1 and 1, this is going to be output is 0, right? So in this particular case, as you can see, if j is equal to 0 and k is equal to 1, the output for q is going to be 0 and q bar is going to be 1. Okay, so you can just practice it one more time, that how it is working on your own. So this is going to be the outputs if j is equal to 0 and k is equal to 1. The other that we can try out is the reverse case, where j is equal to 1 and k is equal to 0. So here also we are going to take j is equal to 1, k is equal to 0. There is an inherent clock that is being supplied. We are going to take this as 1 and 1, only consider the times when they are enabled, and so that the NAND gate does not create a configuration with an R and S both equal to 1, right? So we are going to consider this particular setting of things where j equal to 1, k is equal to 0, clock input is also going to be 1 in these NAND gates. Now similarly, you can have the same thing done here, just in the other, just flipped, right? So q bar comes here and q goes downwards to k. So this is q. Okay. So similarly in this case also, you can see 1.1 q bar is going to be q bar only, and you are taking a complement of that, so this becomes q, correct? And here we have to see that this is actually q bar, right? And we can kind of q dot q bar here. So this is an input which is ANDed, rather NANDed. So q and q bar is going to be 0 and the NANDed value is going to be 1, right? Similarly, if you look at the downside, this is q 0 and 1. So this value is going to be anyway 1. Okay, this value is going to be anyway 1. 1 is coming from the top also. 1 and 1 is 1. NANDed value is going to be 0. Okay, so this is going to be 1 and this is going to be 0. So as you can see, this is kind of easy to remember. If j is equal to 0, k is equal to 1, the output is also 0, 1. So j equal to 0, k equal to 1, q and q bar are 0 and 1. These are complement of each other. So basically q is being set to 0. If it is the other way around, if j equal to 1 and k equal to 0, in that case q is basically set to 1. Okay, so let us recall j, k and q. We have seen examples of 0, 0, 0, 1 and 1, 0. Okay, so 0, 0 was a hold state, right? Memory hold. 0, 1 was q being set to 0 and 1, 0 is q being set to 1. The next state, right? Once the next time the clock goes, q is going to be set to a new value of 1 or 0 depending on what is your value of j and k. Okay, so let us quickly see this different states that we can have. So there is a set state, right, of the JK flip-flop, and there is a reset state of the JK flip-flop depending on the value of q and q bar, or basically q, right? So if you try to put, let's say 0, 0, j and k are both 0, this is a state diagram. So if you have the set is the current state of the JK flip-flop. If you put j and k both equal to 0, that is a hold state. Same for the reset state, doesn't matter. If you put j equal to 0 and k equal to 0, it is not going to change its own state. Okay, it is going to remain in that state. If you put j equal to 1, which is setting the value of q to 1, if you are trying to do that on a set state, if the current state of q is itself q equal to 1, and if you are trying to put set there j equal to 1, k equal to 0, it is not going to change its state, it is going to remain in the same state. Okay. Similarly, if it was in the reset state, that is j equal to, if it was q equal to 0, sorry, q equal to 0, in this case q was equal to 1. If you put q equal to 0, if it was there, and you are trying to reset that circuit by putting j equal to 0 and k equal to 1, it is going to remain there. No transfer of states, right? Whereas if you try to reset a set circuit, that means that if you are having q equal to 1 and you want to reset it to q equal to 0, then you need to pass on j equal to 0 and k equal to 1 and vice versa. Okay. So you can have j equal to 1 and k equal to 0, which is going to, it is a set command, but if you are trying to put that on a resetted JK flip-flop, it is going to be set. Okay. So this is going to nicely capture the different kinds of conditions that can arise. One more condition that is remaining to be done, which maybe all of you have figured out, was the fourth condition, because remember, in this particular slide, we did not yet mention about what is going to happen in this particular case, right? So we are going to take it up in the next lecture, right? So we have gotten a basic idea of the JK flip-flop for 3 different inputs. One was the memory hold stage, one was the setting it, other one was the resetting it. Then we have one more additional input j and k. We will study that what happens when both of them are equal to 1.